Okay, so today for the BTPC IDEA Series, we have our own Dung Nguyen, postdoc here at Brown University, giving a talk on particle symmetry and composite fermion theories of Jain sequences. So Zoom has been a postdoc here for, I believe, 2 years. Is that right?
Yeah, that's true.
Yeah. And we're really excited to host him today for this condensed matter talk, but hopefully some of the methods and ideas will map onto some ideas in other topics of physics as well. Yeah. Okay, so take it away.
Okay, thanks. So thank you everyone for coming. Today I will give a talk on my very long-term project on particle Hall symmetry and the composite fermion theory of Jain sequence. And it is the work that I did with my advisor, Andre here, and Shivas Goka now at Flatiron, Matthew Robert at Imperial College London, and Tankut Khan now at Central University of New York. So let me dive right in. Okay. So I will give the motivation of the talk. I mean, if very briefly motivation, and then I will be review the previous development for fractional quantum Hall by Jain and other people, and then I will go to the theory of Dirac composite fermions that introduced by my advisor, and then we're showing that there's some distinction between the two approaches, and well, we argue that our approach is a little bit better. Okay, so the motivation. Hall effect is very interesting, and the quantum Hall effect is extremely interesting, and it provides a condensed matter measurement of the relation between the Planck's constant and elementary charge of electron. And fractional quantum Hall is one of the most important and hardest questions of theoretical physics. There's no solution for now, and of course, there's many Nobel Prize. Here is a picture of Edwin Hall. He is the father of Hall effect, but he didn't get Nobel Prize. Here's a picture of von Gliessing. Here is a picture of Sui and Stomer, and both lovely. Three of them get Nobel Prize for fractional quantum Hall. And the last three get work related to fractional quantum Hall, including Tholes, Horden, and Kostelis, and I'm personally interact with all three of them. And if this thing is not yet motivate you, I have another picture showing that why Hall effect is interesting. Let's see. Here is a picture of Einstein, Ehrenfest, Laprin, Honest, West, at Ehrenfest home in Leiden, and they discussed about the classical Hall in superconductor, and well, they get it correctly. When you look at, like, if you can look closely to the picture, you see that there's no Hall effect, no classical Hall effect in superconductivity. Well, just because of the Meissner effect, there's no magnetic field inside superconductor. However, recently, well, not recently, but like around 20 years ago, people suggest BCS theory of quasi-particle in the nu equal to phi half fractional quantum Hall. So that means you cannot have the Hall effect in superconductor, but you can have the superconductivity in the quantum Hall system. Okay. So here I will give a very brief review of quantum Hall effect. So we can think of the integer quantum Hall system as a system of free electrons in the magnetic field. If we consider 2D electron gas in applied magnetic field, and we measure the Hall resistance, you will see there's some plateau here. suggest that the whole connectivity is quantized with the integer number. Nu here is integer. Basically, you apply the current in, and you measure uh, the voltage in the perpendicular direction, and you see that you can calculate the resistivity from this measurement, and you see that the whole connectivity has this quantized value. And in order to explain this result, we can understand this using the free electron model, where with this very simple Hamiltonian, you have the P here is nothing but it's a momentum operator, and A is external gauge field. And you're seeing that with the constant magnetic field induced by this this choice of gauge, the energy of single electron is quantized with this form, and omega c here is the cyclotron frequency. So in this picture, you're seeing that electron will distribute in different degenerate Landau level with gap equal to omega c here. So now, in the semi-classical point of view, you're seeing that electron will go in the cyclotron orbit because of applied magnetic field, and the number of available orbital orbit for each Landau level equal to the total number of flux divided by the value of the quantum flux. So here at each Landau level, you have the electron density equal to the total number of flux divided by the total area, and is equal to the magnetic field divided by the quantum flux. Now, if we apply, sorry, here should be electric field. If you apply an electric field E, you're seeing that due to the Lorentz force and apply force due to electric field, the X electron orbit will have the drift velocity with this form. And from this drift velocity and with the charge density, you're seeing that we can have the electric current density, and we found the whole conductivity with this form, where the nu here is the filling fraction divided by the number of electrons divided by the number of total flux, and it's also equal to the number of electrons divided by the density for a single Landau level. So here is a very simple explanation for the integer quantum Hall result. Do you have any question?
I have a question. So on the previous slide, you used the gauge choice. So is it right to think of this as like a p minus an x and then squared in some transformation of variables? It looks like harmonic oscillator states, but
yeah, it's harmonic.
But if they're not localized at a specific point in space, right?
Yeah, it's not localized. Yeah. So depend on the gauge choice, you can see that you have the wave function is like it's a line in x direction, or you can choose the symmetric gauge. As in this picture, you see that the electron can make a cyclotron orbit in this way.
Got it. Thanks.
Okay. So we finish with integer quantum Hall. Now we go to the fractional quantum Hall. So the story is that the X Landau level has a huge degeneration, and basically you're seeing that if the Landau level is partially filled, you don't know where the electron will stay. So here is the blue is the position of electron, and the y is the available orbital. And because of the degeneration, you don't know where the electron will stay. However, if you turn on the interaction between electrons, in this case, general form, but physically it should be Coulomb interaction. And due to the interaction, we can leave the degeneracy. And you're seeing that in this picture, you're seeing that with the interaction, even the Landau level is partially filled. You can still have the unique ground state. And from that, you can see that the whole constant is also fractionally quantized, where the nu here is fractional number. And basically, this is not the end of story. When you think about the problem at the lowest Landau level, you're seeing that you need to consider very strongly interacting problem. We can go to the lowest Landau level in the following way. So basically, you have two energy scale. One is cyclotron energy, is a gap between Landau level, and another is the average Coulomb interaction, and with this form. And here I use I put the LH check, the elementary LH check equal to 1, and you're seeing that the Coulomb interaction is proportional to 1 over LB. It is a average distance between electrons, and you see that you have two energy scale to compare, and there are two mathematical equivalent way to achieve the lowest Landau level limit, where the Coulomb energy is much smaller than the cyclotron energy. So in this way, when you compare this, you see that n divided by square root b is much smaller than 1. So you can take the limits, either you put the very high magnetic field, or you take the massless limits of electron. And after you take the lowest Landau level limit, you can forget all the higher Landau level and study the physics of lowest Landau level only. Yeah. So in the lowest Landau level limit, since the all of the electron have the same kinetic energy, effectively there's no perturbation theory that you can use to study this problem, because you have no small parameter. So in the usual electron problem in, for example, Fermi-liquid, you can say that you can use Hartree-Fock approximation because the interaction is much smaller than the kinetic energy. However, in this case, it is the opposite direction, where the own kinetic energy are suppressed compared to the interaction. So the only solution so far, only direct solution so far, is the numerical calculation using exact diagonalization, and the limit number of electrons that people can do is about 24, I think, is the maximum, and it's far from the thermodynamic limit. That's why many numerical results are skeptical by other people. And in the talk so far, I will only interest in the filling fraction close to 1/2. All of these filling fractions are observed experimentally. Here you have 1/2, you have 7/13, 6/13, and they are like particle hold dual to each other. So you see that the summation of this filling fraction and this filling fraction, you will have the result equal to 1. Yeah, so here's the main interest of my talk, with the filling fraction n divided by 2n plus 1 and n plus 1 divided by 2n plus 1. Here half filling. Okay, so in order to understand the problem of fractional quantum Hall, there's many approaches are proposed, and the most successful so far, approach so far is flux attachment, induced first by Nguyen and Halperin, and then by other people. Well, I gave the same talk in front of Halperin and Hansen. They wouldn't agree with me yet, so I hope that it's not that bad. Okay, so let me review the flux attachment approach. Remind that we have this Hamiltonian of electron in magnetic field with interaction in the second quantization language, and yeah, in the rest of the talk, I will use the natural unit in this form, and you do the flux attachment. You attach two flux to electron using the following transformation. You define the new field per side, can derive from the electron field by this transformation. Here, rho x prime is the charge, is the electron density at position x prime, and theta x minus x prime is the angle between x minus x prime and the x-axis. And you're seeing that with this extra factor, when the new particle per side go around other particle, it's gain Aharonov-Bohm phase with equal to 2 multiplied by 2 pi. So because of this transformation is unitary, you're seeing that the density operator of electron equal to the density operator of the new particle per side. Okay, do you have any question? Good. Let's move on. And so you're seeing that you using this gauge transformation, you change you transform your Hamiltonian S to S prime, in which the new field, we call this is composite fermion field, not only sees the external magnetic field, but it also sees the immersion field, such that the magnetic field induced by this immersion field equal to the charge density. So this charge density here is equal to the electron density, and is also equal to the composite fermion density, because the transformation is unitary. And here is the number of 2 here, because we attach 2 quantum flux to each particle. So that's why the approach called the flux attachment. Okay, so S prime is Halperin, Lee, and Reed Hamiltonian, and beside here is a composite fermion field. In this step, you're seeing that we replace an electron by a composite object, include a composite fermion and 2 flux with opposite direction with applied magnetic field. At this step, the transformation is unitary and exact. We still treat the composite object as one electron, and basically we did nothing. And the density of the composite particle equal to the density of electrons because of the unitary transformation. However, well, we still can show the SLR Hamiltonian without a mean field approximation, which is ambiguous and problematic. So how we do that? In this approximation, we say that the emergent gauge field takes a rate value and spread out from the composite fermion to produce the extra magnetic field. And now the composite fermion sees the effective residual magnetic field with this form. So the picture is following. From the previous step, we replace electron by the composite object with two negative flux. In this step, we're saying that the two negative flux will spread out from the composite object and cancel part of the applied magnetic field. So this thing is the mean field process, and basically you're seeing that using the mean field approximation, the composite fermion will see less magnetic field, and they will form integer quantum hole of the composite fermion. That's why it's a solvable problem, because at this point we can say that composite fermion will have finite kinetic energy. It feels different Landau level, and then we can do the perturbation theory. So let's take a look at this picture. You're seeing that the filling fraction of electron is 2/5, where you have 4 electrons and total 10 flux. Here, if you add 2 negative flux per electron, you will see that at this mean field picture, you see 4 electrons and 2 flux. So that's why the composite fermion will have the filling fraction equal to 2. And basically, it forms the integer quantum hole of the composite fermion. So here is a more general picture. If you have the filling fraction of electron equal to n divided by 2n plus 1, you will see that the composite fermion has the filling fraction big N. And here we see, we consider the particle hole dual of this filling fraction with the filling fraction 1 minus nu p equal to n plus 1 divided by 2n plus 1. You see that the composite fermion, in the composite fermion picture, you're seeing that they fill the Landau level with the filling fraction minus n plus 1. So basically, with this approach, you transform the fractional quantum hole problem of electron to integer quantum hole problem of composite fermion. And in this composite fermion picture, you have some hope to do the calculation.
So in your previous slide, you said that the mean field treatment was kind of problematic.
Yeah, because basically the thing is that you have assumption, a very non-trivial assumption on the strongly interacting system.
And that's that the fluxes kind of spread out and cancel each other out, even though they're pinned to the locations of the electron.
Yeah. So the approximation saying that you spread out the flux to cancel part of the external magnetic field is a problem, because you don't know that if it's true in the real physical system. So basically, you have an assumption about the ground state of strongly interacting system. Very, very non-trivial. So from this step to this step is exact, but from this step to this step is not exact. And it's like assumption.
But it was historically, it was considered a pretty good idea because it gave you the right geometry for the fractional quantum Hall states.
The following issue happened. Here you're seeing that the composite object like includes the electron, includes the composite fermion and two flux, right? So basically, it's the dynamic of electron. At the dynamic of composite object will have the dynamic of the external flux. If you do this like honestly, but here you're saying that the two flux are spread out and become static. It doesn't move with this composite fermion.
So can I also think of this like maybe physically as I expect the ground state to have, you know, at least in some approximation, roughly uniform density of the electron, the original electrons to begin with. The composite fermion, I composite fermion them, and then that leads to some kind of a uniform density of this emergent gauge field.
Yeah, that's true.
So you wouldn't expect, or yeah, I guess some bizarre kind of translational symmetry breaking state for the ground state.
Yeah.
Thanks.
Yeah. So basically, if you're saying that like if you don't want to understand the dynamic of the system, then you're saying that well that is okay. But if electron can move, then why you can allow the attached flux have the background only?
Jung, this is Jim Gates. I have a question about these composite fermions. Are they considered massless quasi-particles or massive quasi-particles?
So basically, the story is that it's the electron side to the lowest Landau level limit. We assume that electron have mass, have zero mass to go to the lowest Landau level limit. However, in the composite fermion side, there's no proof, but there's a argument that due to the interaction, one can generate the effective mass for composite fermion.
Thank you.
Yeah. Okay. So now there's some success of the flux attachment process. So first of all, it predicts the fractional quantum Hall gap. So in the previous picture, you're seeing that the fractional quantum Hall gap can be considered as the integer quantum Hall gap of composite fermion. And at the filling fraction exactly equal to 1/2, you're seeing that the composite fermion see no residue magnetic field, no effective magnetic field. And basically, fermion with finite density see no magnetic field, they will form the Fermi surface. And basically, the picture of quasi-particle above the composite Fermi C is observed experimentally. So in this work by Wu Kang at Chicago and companies, they showing that actually the composite fermion can be observed in experiment. And with the same, with the expected physics. So when you go like a little bit away from when you go a little bit away from 1/2, you're seeing that the composite fermion will see very, very small magnetic field. And that means it has the cyclotron orbit with this form. So here is the Kf is nothing but it's the velocity of the fermion on the Landau on the composite fermion on the Fermi surface. And from this, you can calculate that if this velocity with this magnetic field, what is the classical, semi-classical trajectory of this thing? And you see that they can see this this like very big cyclotron orbit of the composite fermion when the filling fraction is close to 1/2.
So that's not a, when they say close to 1/2, this doesn't mean like 4/9. This just means like a very small perturbation from the 1/2 level.
Yeah, very small. Yeah. But basically you expect that if you think of the quasi-particle as an electron, you will expect very small cyclotron orbit. But in experiment, you see that the quasi-particle with very large cyclotron orbit, and they argue that's because of the composite fermion see very small magnetic field. And that's why they agree that the composite fermion is actually the physical object that can be observed in experiment. Okay, and now let's talk about some problem of this approach. You're seeing that you have the fractional quantum Hall gap, but using the Landau level language, you're seeing that it should be equal to effective magnetic field divided by electron mass, because from the previous effective Hamiltonian, when you do the unitary transformation, the mass doesn't change. So basically, this thing should be the same mass as electron, and this formula have no reflection of actual energy scale is Coulomb energy scale in the lowest Landau level. We say that we forget about the higher Landau level. And basically with this picture, there's no natural way to achieve the lowest Landau level limit by taking mass go to 0. So the solution so far that you replace the bare mass with the effective mass and can be considered as a renormalized value of the mass under the RG flow. And M star is a phenomenological parameter which depends on Coulomb interaction. And this thing is a non-trivial assumption of the strongly interacting system at low energy. So this will answer Jim's question. So the M star here is, there's no control way to calculate M star, the mass of composite fermion. And there's another issue with composite fermion picture using flux attachment. It is an issue of the particle Hall symmetry. And after you project to the lowest Landau level, particle Hall symmetry, it's the exact symmetry since the Hamiltonian only has interaction term. And the particle Hall do a transformation when transform the free fraction nu to 1 minus nu. So here is the transformation where the position of electron will map to the position of the Hall and vice versa. And another thing is that the particle Hall symmetry was confirmed by numerical calculation. And the consequence of particle Hall symmetry is that this thing is very trivial. So the charge density of the free fraction nu plus the charge density of filling fraction 1 minus nu equal to the charge density of the total total 1 filling fraction 1 and equal to b divided by 2 pi. And from this formula, you're seeing that the particle Hall dual state have the same susceptibility with this form. And the susceptibility is nothing but the density correlation function, because nu1 sorry, rho 1 is a constant, then any perturbation in rho nu will have the opposite perturbation in rho 1 minus nu. That's why when you want to study the correlation function of density operator, you're seeing that this relation holds. So the density correlation of the filling fraction u equal to the density correlation of particle hole dual with that. And furthermore, you're seeing that the whole conductivity at nu equal to exactly 1/2 here need to be exactly one half of the whole conductivity of filling fraction 1. And the whole conductivity of filling fraction 1 is calculated previously. And so basically you're seeing that if nu equal to exactly 1/2, you should expect this whole conductivity result. However, please. Okay. So however, the Halperin-Lee and Reed theory or the flux attachment theory failed to reproduce the particle hole relation of electromagnetic response. So both of these two relations are violated by the flux attachment theory. And the
Sorry, can I ask real quick what you mean by
sure.
particle symmetric disorder? Is that so? Is that completely obvious there that that the disorder in a physical system should be particle symmetric with respect to this emergent particle hole symmetry?
Good question. In the real physical system, it's not manifest particle hole symmetry for the system with disorder. However, here is a mathematical question. If we assume that the disorder also have the particle hole symmetry, will not violate the particle hole symmetry, then the result should have the particle hole symmetry result. However, the previous approach, the flux attachment approach, will not provide the result that you expect.
Great, thanks.
And basically, the calculation so far mostly ignore the contribution of the disorder. And well, there's some different proposal to fix the problem of the particle hole symmetry. And the Dirac composite fermion theory is one of them and is the most successful approach so far. So here is the effective theory of the Dirac composite fermion model. It's idea by Damson. And in this effective Lagrangian, the psi here is the Dirac fermion field in 2+1. And here you also have the emergent gauge field. And big A is the external background field. And the N you will have the Coulomb interaction of electron. So there's some key ingredient of this model. The Dirac composite fermion are neutral. So here you see that it doesn't couple directly with the external electromagnetic field. It's only coupled with the emergent gauge field. This is the first point. Second, you can use the equation of motion of emergent gauge field, so that we have some constraint. So when you use the equation of motion of A0, you will see that the composite fermion density equal to the external magnetic field induced by this term. Furthermore, you see that the composite fermion current will equal to this form. Like it will related to the applied electric field. That is nothing but equation of motion of small ai. So here is a constraint induced by the equation of motion of small a. And the thing is that you can show explicitly that this Lagrangian is preserved, is particle symmetry preserved. And here we introduce the VF. It's also a phenomenological parameter which plays the same role as M star in the SLR theory. So we're not claiming that we can overcome the problem of effective mass. We're saying that we can so think of this as a phenomenological parameter. So
if I could ask a question,
yeah.
Was the idea here to you start with the normal, the same problem as with the HLR theory, and then by some manner a Dirac quasi-particle comes out of the model under magnetic fields, or is this trying to solve the fractional quantum Hall effect in systems that already have Dirac fermions?
No. So this problem is this problem we want to solve the fractional quantum Hall problem of the original electric field at original electrons. However, we from the previous approach using flux attachment, some issue happen. The particle Hall symmetry issue happen, and here the idea is propose a new effective theory that solves the problem of fractional quantum Hall of electron. Not to solve the problem of fractional quantum Hall of graphene.
Okay. Thanks.
However, in a paper with Andrei Gromov, I showing that the lowest Landau level problem of graphene and the lowest Landau level problem of electron are dual, like identical.
Right.
So basically, the reason you're seeing that when you write down the lowest Landau level problem of graphene, you will see that only one component appear. So you have two components in the two component Dirac Feynman field. But when you do the lowest Landau level, the only one component appear, and the one component appear in the wave function is the same as the lowest Landau level wave function of original electron. So the two columns are the same. Okay. Okay. So so this thing is the original proposal by Damson, and now I will show
Sorry,
some.
can I ask just real quick? Is there a particular reason to not include a Chern-Simons term for little a?
Yeah. So if you ask the Chern-Simons term for little a, you saw that the particle Hall symmetry is violated.
I see. So a transforms under particle symmetry?
Yeah. The small a and big a transform under the particle Hall symmetry differently. But in the paper, in this paper by Cern, he showed explicitly that if you include the Chern-Simons of small a, then you will violate the particle Hall symmetry.
I see. Yeah. Thanks.
Can I, this is Jim. The last term I have a question. Is this somehow associated with some non-locality or not? The last term.
The last term, yeah. So the Coulomb interaction is non-local. It's long-range interaction.
Thank you.
In 2 dimensions. Yeah. And basically the thing is that the Coulomb interaction comes from the 3+1 Maxwell field. And with the 2+1 dimension, you have no way to renormalize this. So basically, it it cannot be trained to coefficient. Okay, so here I will show some contribution to the Dirac composite fermion. Okay, so in this paper we investigate investigate the theory of Dirac composite fermion more, and we're seeing that the Dirac action is not invariant under the Galilean transformation in the flowing form. You will do the Galilean boost on the system, and you're seeing that this term is not invariant under the boost. So basically, we need to change the time derivative term by adding extra term. By adding this extra term here, B is applied magnetic field, is constant applied magnetic field. You're seeing that this term under the Galilean boost, the electric field also transforms, and this combination is invariant under the Galilean boost here. Well, you're seeing that with this transformation, when you take the time derivative, you're seeing that it also hits the transformation of coordinates, and you're seeing that you need to have the derivative in x to compensate with this time derivative. So basically, this thing is the extra term that we introduce to preserve the Galilean transformation, which is expected symmetry of the non-relativistic problem. And with this extra term, you're seeing that you have the electric field coupling with the momentum of the composite fermion. So basically, we're saying that this thing is nothing but it's a dipole moment coupling, where the dipole moment perpendicular to the momentum of the composite object. So basically, physical picture is that Dirac composite fermion is neutral. It doesn't couple directly to external electromagnetic field, but it has dipole moment which couple to the external electromagnetic field. These features were missed in the first proposal by CERN.
So is that because there's like excitations maybe in the Dirac fermion, because it's moving in time? You're seeing like this diagram on the right, or?
So well, sorry, maybe I explained it not very good. So basically, I'm saying that in the Dirac composite fermion you have this term, right? The time derivative term. And basically, I'm saying that if you consider this transformation as the symmetry of the action, like if you do the Galilean boost and you're saying that under the Galilean boost, the action should be invariant.
Yeah, so I understand like mathematically why that term has to be there, but is there like a physical description of where the dipole term is coming from? Yeah.
Yeah, so physical description, you can think of this as, well, it's very easy to explain in terms of the flux attachment. Basically, the thing is that you can see that with this like very naive picture, you're seeing that here is the two flux with the electric charge plus E, and here is the electron with the electric charge minus E. So if you attach two flux to the electron, and basically when you move in the magnetic field, you will have like the Lorentz force that makes so two flux and electron have the opposite charge, and they have the Lorentz force opposite to each other. Then they want to separate, but the Coulomb interaction makes they want to like closer. And the balance of this thing will give you the picture that the dipole moment should related to the velocity of the composite object.
Got it. Perfect. Yeah, thank you.
So this thing is just like picture that I made up, but it should be related to the interaction more. Well, it should be more complicated. It's just a picture, but it should be more complicated. So basically, for the filling fraction equal to 1/2, you can show that the flux, the quantum flux, have the electric charge equal to 1/2 E plus. And so when you attach two flux there, then you're seeing that the two flux will have the total electric charge equal to 2 plus E. And the composite object, when it moves to magnetic field, it makes the dipole moment. Okay, let's move on. And so when we consider the Jain state near 1/2, it's also shown, we can also show that the Jain state of electron near 1/2 will map to the integer quantum Hall problem of the Dirac composite fermion. Because of this relation, so here is a constraint, and here is the charge density calculated from the action. You're seeing that with this filling fraction, you can calculate the composite fermion filling fraction, and it's equal to n, big N plus 1/2. And you remember that because of the it is a Dirac, the composite fermion is Dirac, then the integer quantum Hall of Dirac will have the filling fraction integer plus 1/2. So basically, with this both filling fraction of electron, you will map to the composite fermion with opposite side, and both are integer quantum Hall problem. And basically, you're seeing that from this picture, the two particle Hall dual filling fraction will map to the Dirac composite fermion picture with exactly the same with opposite side filling fraction. So this thing is a particle Hall symmetry in the Dirac composite fermion picture. And when you look back to the flux attachment approach, you're seeing that this filling fraction will map to the composite fermion with filling fraction n. And this filling fraction will map to the composite fermion with filling fraction minus n plus 1. So that is a signal saying that the particle Hall symmetry is violated in the flux attachment approach. Okay, so with Jain state near half filling, that means the last n limit in the composite fermion picture. And basically, the composite fermion picture, the Dirac composite fermion will also form the Fermi-liquid in a weak magnetic field. So basically, we can recover the picture of the composite Fermi-liquid, which is a success of the flux attachment theory. We also can have the same thing. And in the last n limit, we can perform the semi-classical calculation and open the closed form result. And that we will do. Okay, do you have any question at this point?
Sorry, so this n, how does it show up in the Dirac Lagrangian?
It doesn't show up in the Dirac Lagrangian, but basically the thing is that even in the electron problems, and it doesn't show up. The filling fraction here is that saying that you have background magnetic field, and you have charge. You have the background charge density.
Yeah. So I guess I'm just asking for this kind of a large n picture or a large n calculation. typically I expect some n floating in the Lagrangian, right? So here it's a slightly different style of large n calculation in that the large n shows up in what state you're perturbing around, right?
Yeah,
'cause-
so the last n showing in the following way. You think that's the filling fraction of composite fermion which is formed, right? N plus 1/2. So the filling fraction of the composite fermion showing that the ratio between the charge density of composite fermion divided by the emergent magnetic field background. So when the density is much bigger than the magnetic field, you think that you can study the story, you can study the theory of Fermi-liquid of the composite fermion in very small magnetic field. In this way, you can do the semi-classical approach. And you can do the semi-classical approach. And in my paper with Andre Gromov, we're showing that the semi-classical approach gives the same result when you do the field theory calculation using the random phase approximation up to leading and sub-leading order in 1 over big N.
Great, thanks.
So we show that explicitly that the last N limit is important here, and we're showing that the semi-classical and field theory calculation give me the same result up to some order of 1 over N, 1 over big N. Okay, so here is the semi-classical picture, and we saying that the low energy mode of the composite fermion sector as a perturbation, as a deformation of the Fermi surface. So we have the U0 is the dilatation when you change the area of Fermi surface, and U plus and minus 1 so the shift left or right of the Fermi surface, and here is a higher spin mode. And remember that you have the constraint before. So the composite density needs to relate to the applied magnetic field, and the composite fermion current needs to relate to the electric field. So that's why the dilatation mode and the translation mode are constrained and they are non-dynamic. However, all of the higher spin mode are dynamical.
So here, when you have this, the subscript indices on the U, does that correspond to the effective Landau level of the theory?
No, it's not. It only, so all of the excitations that I'm studying is lowest Landau level excitation. There's no higher Landau level here. So basically, you can think of the U0 as a charge density. So it's like per psi dagger per psi.
Mm-hmm.
U plus, U minus 1 is like per psi dagger dz per psi, or per psi dagger dz bar per psi, where
Okay,
G
so,
and G bar are complex conjugate. And here is nothing but per psi dagger dz square per psi.
Okay, so these are the higher order moments. Okay.
Yes, that's correct. But the point is that the low energy excitation is nothing but is a deformation of Fermi surface. And because we ignore the dilatation, then all of the excitation here as the deformation, but preserve the area of the Fermi surface. And it's just saying that we do not allow to change the composite fermion density because it's here equal to applied magnetic field.
Sorry, maybe a little tangential, but
yeah.
I mean, I mean, it sounds a lot like the Ledinger theorem for kind of regular Fermi surfaces.
Yeah, that's true.
But it seems completely logically distinct, right? Just
yeah.
okay.
So basically, you can do the different ways. So this thing is like bosonization language. In the composite fermion picture, you have the fermion field per side, right? But here I formulate all of the excitation as the per side dagger and some derivative per side. So all of the excitation are boson. So it's a fancy way to bosonization a Fermi-liquid in 2+1 dimension.
This might be a sorry, this might be a silly question, but basically what this is saying, what the bottom part is saying is that the constraint from the first constraint from the Dirac composite fermion model prevents like instabilities in the higher spin modes. So for instance, like if you'd be interested in like a topological instability type thing, that is prevented from this first constraint. Is that, am I interpreting that correctly?
So the interpretation of the constraint just saying that you have, so basically if you don't have this if you don't have this constraint, then basically you can have the dilatation and the translation mode as the dynamical mode. But with this constraint, they cannot be dynamic. So basically, basically the thing is that this thing is a Fermi surface for one point in the coordinate space. You can have different Fermi surface in different point in the coordinate, and so this thing is nothing but saying that you do not allow to have different composite fermion density at different position, two different position on space doesn't have the different density.
Mm-hmm.
Yeah. So basically, when you study the usual Fermi-liquid without any constraint, you can say that you can have the density wave where the charge at this point different with the charge at this point, and when you transform this to the language of distribution function, you can say that the integral of the distribution with the momentum will give the different result at different coordinates. But here, because of the constraint, you do not allow to have this.
Jim Gates again. I have a dumb question here too. So when I look at this diagram that you're showing, it immediately makes me start to think of higher spin. If I try to construct an effective field theory, it starts me to thinking about higher spin effective field theories.
Yeah.
Are there such descriptions available?
Just this here.
Ah, okay. Thank you.
So here is effective Hamiltonian of Dirac composite fermion sector. You see that's UN and higher spin field. And Fn here is nothing but phenomenological Landau parameter. And we have this commutation duration of higher spin field. And here B bar here is nothing but it's a background of emergent magnetic field. And N here is number of the higher spin field. And basically, there's different way to open this commutation relation. One way is saying that the UN come from the psi dagger dz power of n psi, and then you use the commutation relation of psi. You use the anti-commutation relation of psi, and then you can derive something like that. Or you can, well, you can use the Boltzmann equation to derive the same result. So in the paper with Andre Gromov, we do that. We do the Boltzmann equation and we obtain the same result. And here, yeah.
Yeah, I'm good now. Thank you.
Okay. So basically here, all of the, because of this commutation relation, you can show that all of the mode n have the gap like this. When omega star is like, is, well, it's the same as b bar divided by m star, because kf divided by bf is nothing but m star. Well, and now you're seeing that if you say that fn equal to 0, this thing is nothing but saying that different mode correspond to different composite fermion Landau level, and it's, well, I think that is why Stephen asked the question. So here, energy of different Landau level.
Yeah, exactly. Yeah, exactly.
Yeah, exactly. And well, we have the bosonide model, and because you see that we have the quadratic theory with respect to the UN field, and the commutation duration is linear, then that's why this model is exactly solvable. And then we can calculate the electromagnetic response in closed form. Okay. So now we will show that one can use the bosonization language to study the neutral excitation in the fractional quantum hole, which people call the magnetoroton mode. And this mode was proposed numerically by Gervin, McDonald, Plasman, and also Howden and Ed Rizai.
I should also say that Zoom, it's been about an hour. We have been interrupting you with questions, but maybe try to wrap up in about 10 minutes.
Okay. Hopefully I can do that. So, well, so the magnetoroton mode in the fractional quantum hole now becomes the UN mode in the Dirac composite fermion when n bigger or equal to 2, because 0 and 1 constraint. So basically we can solve the Hamiltonian, and you're seeing that dispersion relation will satisfy this equation where U tilde is omega divided by omega c star, and Q here is the momentum. LB is magnetic length induced by big B, and big N is a parameter in the model in the parameter of the Jain filling fraction, and J here is nothing but the Bexel function. So here is the solution of the Bexel function. You're seeing that it gives us the dispersion relation. It's the tilde, and it's the relation between tilde and momentum. So here is the dispersion relation. But at this point, I didn't introduce the, I'm saying that there's no Coulomb interaction, and I set on the Fn equal to 0. Okay. However, for more realistic result, we add the Landau parameter Fn, and here is the dispersion relation. If you add the Landau parameter Fn, you see that the plate that it the frequency go to 0 is the same as before here. The position here and the position here is the same. When you add the parameter Fn, it doesn't change the point that the dispersion go to 0. And so if you add the Coulomb interaction, you're seeing that because of band splitting, the dispersion will form some minimum. And we expect that if the Coulomb interaction is not so strong, the position of the minimum is also the same as this position. And basically, it needs to satisfy this relation. So that means the position of the minimum should be the root of the vector function J1. And now let me show that it satisfies in experiment. Yeah. So here is so this thing is experiment for the magnetoroton dispersion relation, and the dashed line is our prediction, the root of vector function. This thing is for 4-9 state, and this thing is for 3-7 state. So that is it's quite close. Here is for 2 results for 2/5 state. So this thing is the result in the work by Pinchuk and work by Kukuski. So here 2/5 here, and here we also have even 2 value of the minimum. So it's much perfectly good within 10% of the experiment result. And when you think about that, you see that you see some root of vector function in experiment. It's very non-trivial. And even for nu equal to 1/3, you see that that's quite close to the experiment result. Yeah. So the lowest magnetoroton is the U2 field with spin 2. And basically, we expect that the spin of the excitation can be determined experimentally by polarized Raman scattering. And it's a work that I'm doing with my advisor and Kun Yang at Florida, Holden at Princeton, and Ed reside at California. Okay. And let me go through. Yeah, so basically the last part, I'm just saying that we can reproduce the electromagnetic response and so that it satisfies the particle Hall symmetry explicitly. And there another issue that happened with flux attachment theory when we study the project statics, when we study the static structure factor, which is nothing but the equal time density correlation function. We have this form where S here is a when Z shift, and basically Holden proposed an idea that the coefficient of Q to the fourth of the static structure factor need to be bigger or equal than this value. But the flux attachment approach violates both of them. Then that's why there's also the problem with the previous approach. And here's the conclusion. The Dirac composite fermion predict precisely the dispersion relation of excited mode in the lowest Landau level. We saw the sharp distinction between the Dirac composite fermion theory and the SR theory. Basically, that saying that the particle Hall symmetry is violated by the previous approach and preserved in our approach. We derive the electromagnetic response of Jain sequence, and basically we saw that our theory satisfy the physical requirement for the effective theory of lowest Landau level, like particle Hall symmetry, Gaussian invariant, and etc. And the outlook, we can also study the Dirac composite fermion of 1/4, 1/6, or 1/8, etc. And the reason proposal for this theory are violate the Holden bound that I briefly said. And in our coming work, we show that we can have the Dirac composite fermion theory for the Jain sequence near different filling fraction. We also study the bilayer quantum hole with a filling fraction with two particle hole to a Jain state. And this is work in progress with people at Oxford and Harvard. And also the question is the Dirac composite fermion of the for graphene. There's also the strongly support experiment in this one, showing that the composite fermion model for the fractional quantum hole in graphene should be also Dirac. Well, and our theory also propose experimentally check for the fractional liquidity in 2+1 dimension. That's all. Thank you.